So one thing is that at IIT Gandhinagar, or for that matter, at most of these institutes, we are very particular about time. Right. So please make sure that you come to lab sessions as well as tutorial sessions and lectures on time, because we'll start even if one single person is sitting in classroom. Okay. So you may tell to your friends if you have made any during this workshop to be on time so that we can have healthy discussions and learn something, right? That's why we all are here. You and me, both of us are here to learn some new things. All right. So let's talk about our new topic, which would have some of the takeaways from our talk yesterday, but we'll try to learn something that what is now existing in real space in terms of data, how we use data, and I will show you one specific application of that particular data. We'll first of all try to understand what these data sets are, and then in lab session you will actually work on these particular data sets. I did not want to make any hyperbolic statements that we have petabytes of data, we have complex data and so on. I really want you to see that data, explore that data. I'll also show you from where we download that data, so that when we finish our discussions today, you have little more confidence that these are the things that are now really in action, just beyond theory or just beyond academic exercises. Does it make sense? However, before we start playing with data, first thing we should know from where our data is coming. What are the generational processes that are generating that particular data? Why, what are the uncertainties associated with this particular data? How we try to capture that data? And beautiful thing about our discussions today, it would not only apply to climate models. Uncertainties we are going to talk about will apply to almost all the data generational sources we have, right? Not necessarily all sources of uncertainty, but out of three, two sources of uncertainty will definitely apply, and one is very specific to climate systems, which is internal variability. But every system again has variability, so to some extent it will also apply. So please pay attention. You will learn something, that is what I can guarantee. But for that you have to pay attention to. These are new topics for all of you. I will try not to overwhelm you, but still convey the message and complexity with enough clarity. At any point, if you have any questions, please feel free to ask. Sounds good? Again, same rule applies. If you don't need to use laptop at this point, it's better to turn off the flap. Otherwise, you will always be distracted, right? Or everything can wait, but when you are in classroom, it's always better to pay attention to what we are talking about. Okay, so let's talk with eye contact. I don't want to see your hair when you are working on desks, right? Eye contact is always better. So today we are going to talk about deep learning and computer vision models for generating high resolution climate projections. This is our end goal, by the way. We will use deep learning and computer vision to generate high resolution projections today. Okay, but before that, let's see what these word means, climate projections and so on. Before we really, and again, participants who are sitting online, as you did yesterday, please feel free to type. I would be reading almost everything in real time. If you have any questions, please feel free to do so. I may answer the question if I have a clear answer. Otherwise, I would take that question away and then come with an answer if I don't have ready-made answers, right? So that's how we will proceed. Before we even start talking about technicalities, today I am going to talk about climate and not weather. So what is the difference between climate and weather? So precisely, weather is something that you get instantly, right? What you have outside is weather today. Climate is estimates or expectations over long period of time. Not estimates, but expectation over long period of time. Warm summers, cold winter, right? Wet monsoon, dry monsoon. When we talk terminologies like this, we are typically talking about climate of that particular place. Yeah, summers are warm, winters are cold. So I'm not talking about tomorrow. One day in summer can be cold also, one day in winter can be warm also, right? So there is always a variability in the system. But if I look outside window and I see that it's raining, then I'm reporting weather, not climate. Although as general public, as laymen, we often use these terms interchangeably, especially when we say the same thing in Hindi, both becomes Mausam, right? But in engineering, in scientific language, both of them have serious distinctions. So again, climate is what we expect over a long period of time. So we were not trying to predict what is going to happen tomorrow. We are not going to predict what is going to happen day after tomorrow. We are interested in long term statistics, that what is going to happen over next decade, next 5 years, next 30 years, next 60 years, 90 years, and so on. How many of you follow cricket? Not many. How many of you have seen matches in England? What happens? Not there, on TV also. Most of the time it rains, right? And then people get upset. Why can't they predict what is going to happen after 10 days before scheduling a series? Today we'll leave this room with an appreciation why this problem is so difficult, so hard, why this really cannot be done as of now with the system of equations we have. Tomorrow, yes, forecast would be 90%, 89%, 95% accurate if I talk about tomorrow. But as I keep on going in lead times, I would lose predictability of the system very quickly. However, I can still say that let's not schedule matches in England over month of May because high probability it would rain. But still, I cannot tell on what specific day it will rain. Right? Perhaps no model can tell us when it will rain. So today we'll appreciate that certain things are predictable, certain things are not. And that's why we have to settle with the statistics and keep on improving the model. So that's always given. We are not settling here in the sense that we have accepted that as our fate, but we try to come up with new formulations, new representations, new equations. And that's how we have reached here, but still there is a way to go. Okay. So this is what we are going to talk about. First of all, we have to again see what goes inside the climate. What is this? Why this is like coming like this? I don't know. Okay. This is, see this? Yeah, stop share and share again. Yeah, perfect. So let us first of all look inside what these climate models are. So I'm giving you a 10,000 feet view, an overview that what goes inside this model, keeping complexity aside, but you should be able to appreciate why these models are so complex, what these models entail, and so on. So yesterday somebody asked me a question that climate models give information at one single point, what it means for regional impact assessment. That's what I said, no, I will talk about that. This is what I'm going to talk about. So yesterday you learned about hydrological models, something, right? We try to predict some flow in the river using various variables around us, apply physics, apply conservation of mass, apply some empirical equations, semi-empirical equations, and then try to predict some variable of interest. Same happens in climate model. Again, it's a model. However, here Earth is very large in comparison to basins, river basins that we are studying. Basins will contribute to specific point. Remember the DJ floor analogy I gave. Anything outside that DJ floor would not come and contribute there. So that's why you say river, Kaveri basin, Ganga basin, Yamuna basin, because that basin would only contribute to that particular point. So what we do in climate models is that we have to now model a system. It's an Earth, it's a system, right? And we have put a boundary that Earth is our system of interest. What is system basically? You all must have heard that wherever we have defined boundary, right? And then we try to study it as one holistic unit, we typically say that it's a system, right? And thermodynamics people will define it differently, fluid mechanics people will define it differently, but for us this is a system where we have a boundary defined within which we are studying the processes. It can be open system, it can be closed system. Right now we are assuming it to be exchanging energy and masses with the, I mean, from sun we are receiving energy, we are also giving out energy back to the external space, right? Masses we are assuming that we are conserving in lower atmosphere and upper atmosphere. So far so good. Try to visualize as I speak. Don't try to worry too much about text, etc. Try to visualize as we are speaking. Also, you can imagine that we have earth, we live on the surface of the earth. As you go up, we have an atmosphere. Atmosphere has different layers depending upon its composition, constituents, and so on. And these compositions also change as we go vertically upwards. As you can imagine, layers which are closer to the ground would be more dense because of action of gravity. Also, as a result of which heavier particles will try to settle down. So you would have more oxygen concentration, more nitrogen concentration, or more concentration of air. Density of air would be higher as you are closer to Earth's surface. As you climb mountains, if anybody has done trekking in higher mountains, what happens? We start losing oxygen. This is precisely the reason. Now extend the same thing to 10 kilometers, 20 kilometers, 30 kilometers upwards. So we are dealing with complex system. Let's agree with that. Also, we have oceans, we have land. On land, we have urbanization at certain places. We have plants at certain places. We have rivers, certain places we have lakes, ponds, whatnot. So we have serious heterogeneity all over the place. But what scientists do, they study all these components in isolation first, right? That is, we will develop model for oceans, that how energy and mass balance happens in ocean, how they exchange energy and mass with the adjoining packets of land. So an oceanographer will bring that particular expertise on the table. Somebody working on land ice and sea ice will bring that expertise on the table. Somebody working in upper atmosphere would bring that expertise on the table. Somebody working in hydrology will bring the expertise of land on the table. So people and experts from all over the globe will work on the components that they are interested in, develop the models for them. What are the models? These are dynamical models. You might have heard terms static and dynamic. What is the difference between static and dynamic? Huh? Static, which remains same, they're not function of time essentially. Dynamical, which are function of time, right? So they would have certain quantity x with respect to time, dx by dt, right? And we try to have its functional form. So some functional forms are known again through fundamental equations that govern these particular systems, right? So for example, we know a lot about thermodynamical equations, how heat would flow, rate of change of temperature with respect to time. A thermodynamics person will give us that particular equation. We would also know how rate of mass will happen with the rate of change of mass in control volume, not in system, because system is a conserved mass entity, will happen over time. So we are talking about dynamical system. Now, let's talk about Earth systems. At a particular place, do you think processes are static or dynamic? Mixture of both. But primarily, can we say that most of the processes, atmospheric processes, are dynamic? Wind is flowing. Is wind static or dynamic? Wind is always there, by the way. Even if with negligible velocity, wind is always moving. Otherwise, you would not be able to breathe, right? I mean, sometimes noticeable, sometimes not noticeable, but air is always in motion. Do you agree with that? So it's a dynamical system. Same thing with temperature. When you wake up in the morning, it's cooler outside. During the daytime, it gets gradually warmer, and it's not a step function. These variations happen gradually. Same thing with precipitation. Same thing with humidity. Same thing with winds in three direction. Wind is a vector, right? It has a direction as well as magnitude. So wind will blow in x direction, y direction, as well as vertically upwards, right? That's why you see some rotational effects on wind because it has all the components, and when they act in certain way, we see the vortices and tornadoes forming up because they are converging from different direction, and because of rotation of the earth and so on, they converge and we see those rotational effects. This is exactly what climate models try to do. They try to solve the equations of rate of change of temperature with respect to time, rate of change of available moisture with respect to time, rate of change of wind speeds with respect to time, rate of change of relative humidity with respect to time, right? So we call these as, these systems are dynamical. I am talking about equations because when I say dx by dt is equal to function of something, what is that? It's an equation. Do you think these equations are linear or non-linear? Why? How do you know? Dynamical doesn't necessarily mean it's non-linear. Let us say that dx by dy by dx equal to x. Is it a linear system or non-linear system? Dy by dx equal to 1. Is it a linear system or non-linear system? It's a linear system because you can do the variable separation, do the integration, and you would clearly see that the clear solution is there. When so dynamical doesn't necessarily mean system has to be non-linear, right? But given the complexity that we are dealing, given the formulations we are dealing, these systems are actually non-linear dynamical systems. They change with the time. They are complex convolution of each variables. Why? Because these equations are written simultaneously. As you can imagine, when it's warmer outside, wind speed will increase because now there would be more differential of energy and winds will start flowing from one point to another. So that means there is a driver. So that does that mean that you can separate temperature from wind? No, right? Temperature would influence wind, wind would influence temperature. All of them will influence presence of moisture. All of them will influence relative humidity and so on. So all these are coupled in some sense, and that essentially gives them their non-linear nature. Does it make sense? So we have non-linear systems. We have to solve them simultaneously, right? Because now number of variables are high and all of them are coupled with each other. So these systems are typical example of simultaneous non-linear differential equations. So that makes them immediately very complex because now we are talking about all the complexities coming to meet us. How to solve them? That's another question. So people who are mathematicians, they would find different formulations how to solve these PDEs. Some of them are deterministic in nature, some of them are stochastic in nature, some of them are solved exactly, some of them are solved analytically. But the problem that we are talking here, we always try to find the approximate solutions of this such a complex system, right? So one way to solve them is discretization. I can always write dx by dt as x2 minus x1 divided by t2 minus t1. That's what dx means, right? Small change over small period of time. It's function of something. I can always write x2 minus x1 is equal to that function multiplied by dt. I can always write x2 is x1 plus that function, right? I have discretized the entire system, right? So just to make it a little bit more clear, because this will be important as we go forward. Yeah. So all I'm saying is that if my dx by dt is some function of, let us say x, let's keep it simple, right? It's function of x and t, not a variable separable. It's function of x and t. So far so good. Can I write this as x2 minus x1 upon dt is equal to f of x of t? This could be anything again, x of x, y, z, t and so on. So far so good. Any confusion, please ask. Can I write x2 as f of x of t times dt plus x1? Yes or no? So basically what I have done, I have discretized the system. at the risk of introducing some uncertainties just because of the virtue of time step. This dt has to be infinitesimally small. So that's where they are called as approximate solutions. Now question arises that Earth is so complex, it's not a single point system. So how we go about that? So what we do, we divide this particular Earth into number of grids, as you see on the board, right? And at each particular grid, we apply this conservation of mass, conservation of energy, conservation of momentum, and try to study that what is going out of these particular grids, what is coming in of that particular grid, what is the change in form of mass that is happening, in what form energies are coming. Oceans will have different response to energy, right? If same amount of heat falls on water versus same amount of heat falls on land, there will be differential heating. Why? Because water would need how much joules of energy to raise temperature by 1 degree Celsius? 4.2 kilojoules of energy per kg per degree Celsius, right? However, land may need lesser amount of energy to raise the same temperature by 1 degree Celsius. What that will introduce? It will introduce differential heating. Land will get heated faster. Ocean will get heated slower. So there would be a differential heating. So winds will start flowing from one direction to another. So climate modelers set up equations for that, at what rate this diffusion will happen, at what rate this advection processes will happen, at what rate conduction processes will happen. So that essentially gives us the climate models. Is it clear? Now, as you see that for each grid cell, where oceans are there, where lands are there, where mountains are there, we have different parameterization schemes, different values of constants, even if the structure of equation remains similar. But we are solving these particular equations, and you can now very well imagine the complexity or the data size that we would be generating. No? At each grid, you are applying that equation. You are dividing entire globe into number of grids. You are dividing entire atmosphere into number of grids. There would be exchange between layers of atmosphere. There will be vertical exchange. There would be vertical exchange and horizontal exchange. Oceans. Oceanographers will not study just ocean as a two-dimensional object. There would be a three-dimensional construct there as well, because oceans would have multiple layers inside, multiple layers outside. Then atmosphere will start. I mean, once you go above the surface of atmosphere. So we are really looking into this complexity, and these are essentially computational fluid dynamical models. In this particular class, we are not concerned about running these models. So don't worry that we are running these models. No. And you will very soon realize why we cannot run this model, at least in classroom setting. We can run very, very simple climate models, but modeling of this scale would typically require a supercomputing effort, right? Where all the experts come together, give the equation, set up these equations, set up the parameters, calibrate, validate these particular parameters. So we are not going to do it in an academic exercise. Not only academic exercise, will not run model just for heck of it. There are national labs which are dedicatedly designed to run these particular models. So they will have 5,000 scientists working on different aspects of just these models. Use world's biggest supercomputer just to run these climate models and share the outputs with us, that these outputs are available. But see, it's foolish if we don't understand what data we are using and just using the data. So it's important to understand what these data looks like. Now, when we try to put all these things together, that is vertical flow, horizontal flow together, what you would see? You would see some transfer of mass happening across the globe. So this is these patches or pieces stitched together. And this is how a typical, this is the output from model. You see on top of the earth, certain things are moving. We have just plotted that on space. Right? You see certain cyclones moving there, right? So these basically represent certain direction of flow of masses once we start visualizing these exchange across the grids. Sounds neat, right? So this is output from GFDL, which is one of the climate models that that are run at resolution of 100 kilometers. We'll talk about these resolutions, why we need to do super resolution, what are the challenges and so on. But so far takeaway is that yes, using our understanding of physics, chemistry will also come into action, right? Because we have, yes. Huh? These are not dense clouds. They represent flow of certain mass. Just think of it as a plot. This is just a plot, right? It could be direction of wind. So dense clouds basically represent, so this plot is showing the movement of wind on Earth, right? We are just trying to take a visualization of that, what insides of these models look like. I can also represent them by arrows in x direction, y direction. This would be resultant of those x and y's. Does it make sense? If this makes sense, huh? You have to do it every time. Yeah. You call that class attendant. All right, but we'll not stop our discussions here. Now you might realize that there are grids on which we are applying these equations. That's all we need to know for purpose of this particular class. What should be size of this grid? Okay, very good answer. It will depend on the computing power. Now let me put another question. Let us say that I give you access to all supercomputers in the world. Let's remove that constraint. What should be the size of grid? I want to understand how Ahmedabad would flood after particular precipitation event. So granularity is, I also want to understand what is wind speed at particular location where I am standing right now. So granularity would be decided by the impact assessment that I am trying to do. Absolutely fantastic answer. It should not be. So ideally I would want resolution to be of size of this tile. This is also a grid, right? I can also apply same equation, same processes to this particular tile, which is 1 meter by 1 meter, and want to do it for entire globe. But first of all, we have to think, do we have enough computational power? Of course not. Right? So they would not. So if we double the grid size, or double means make the grid size finer by 2, that doesn't mean that computational power will increase by 2. It will increase multiple folds as you increase the resolution, because again, you are talking in 2 dimension, 3 dimension, vertically downwards in the oceans. So first thing is absolutely determined by how much computational power we have. Second thing is that I may understand lumped behavior of winds. I may understand lumped behavior of solar energy that I am receiving. I may understand lumped behavior of clouds, but I may not have even physics resolved at this particular grid resolution. So what's the point of setting up a model at this particular resolution where I don't have enough understanding of physics? Does it make sense? Third constraint is exactly determined by, I can set up any model in the world, but do I have observations at that particular resolution to even validate my model? Doesn't it make sense? Again, logic coming into picture. I hope you're not climate modelers. Okay, good. Right? So they're not climate modelers in disguise. So they are thinking logically. And that's exactly how climate scientists also think when it comes to determining the resolution. And finally, what we are looking for from our climate models. Would telling an information that this particular tile will flood when it rains, or telling that when it rains over IIT Gandhinagar campus, expect an average inundation of 0.5 meter, 0.25 meter, is that enough for me to do an impact assessment or not? That's precisely what determines the resolution. That being said, 2 cores of a resolution is not very useful. So 500 kilometer resolution. When we talk about resolution, we are sort of averaging over that particular grid size. So when these climate models started, we were talking about resolution of 500 kilometers by 500 kilometers and even more. So we are in Ahmedabad. So there is a hill station 465 kilometers from here, Saputara. 500 kilometers would essentially mean that we are representing climatology of that hill station and Ahmedabad using same approximation, which of course is not very useful. Neither for impact assessment, not even to get the average estimates how climate or weather would look like if you look the time series of that. Does it make sense so far? Same thing, one point in ocean, one point in land, which are 500 kilometers apart, would be approximated by same climatology. Again, not a right assumption. But does that mean we should have never started this exercises? Of course not. We actually started climate modeling from such coarse resolutions. Right, but then as computational resources improved, as understanding of physics improved, as we started learning more and more processes, these grid sizes became more and more finer. So this is the figure that I have taken from IPCC. All of you who are listening to this particular lecture, please note down this term, Intergovernmental Panel on Climate Change. So IPCC is the nodal agency. It also won Nobel Prize actually for its effort to bring scientific community together and develop a platform where all these studies on climate can happen in a cohesive manner, where global labs working on these problems come together, do a common data sharing exercise, and every few years they prepare something called as assessment reports, that how our understanding physical science basis has improved of these particular ideas and topic of climate change, what it means for policymaker, what it means for impact, how different sectors are going to impact, and they do it in very scientific manner, right? Not in a form of that, okay, I have some opinion, let me put it there. They would do some data analysis. Of course, there are certain caveats there. I'm not saying that these would be perfect reports. They should always be taken with pinch of salt, but they still do very fair job in putting things together. Right, so if you see FAR, TAR, SAR, AR4, they represent first assessment report, third assessment report, second assessment report, fourth assessment report. Recently, sixth assessment report came. Right, if you see some boxes there, that's what I talk about grid resolutions. See what has changed between FAR and AR4. FAR was at 500 kilometer. See those green pixels, you cannot even identify what they are. See the same green pixels in AR4. Now you clearly can distinguish the topology and topography of that particular place. Same equations with certain additions of knowledge that we are getting, same equations are. So grids, our sizes are important, and this is what we are trying to do. We will have something of resolution 110 kilometer, which is still not sufficient to do regional impact assessment, local impact assessment. Ahmedabad and Gandhinagar would not share same climatology even if they are 23 kilometers apart. Right, what is happening in Ahmedabad may not be happening in Gandhinagar, because many processes don't operate at such coarser scale. So we would need information at maybe in some cases sub-kilometer scale, less than 10 kilometer, 25 kilometer, depending upon what is the use case we are looking for. Make sense? Now comes that who runs these models? Is running one model sufficient, or we need multiple models? What are your answers? Yesterday we developed one model, right? Hydrological model. So she gave me some variables. I said these are X. I will put as a predictor metrics. I have a Y, which is predicted metrics. I can use machine learning, data science approach. I can use physics driven, completely physics driven hybrid. That's my choice. So she can set up her own model. He said, wait a minute, I will set my own parameter scheme. I will set up my own set system of equations. I will study certain phenomena in more detail than the other. So she can have one model of her own. Somebody sitting towards the end, they may feel otherwise. They may say, I don't necessarily agree with this particular parameters or choice of these particular variables. So I will study this thing separately. I will also include a socio-economic dimension when understanding river flow. I will not just rely on topography and rainfall and so on. I will also include relative humidity. I will also include evaporation that is happening. I cannot deny. It's another model that you have come. Right? Somebody working in India will say that Indian monsoons are most critical for us. So I will study phenomena associated with Indian monsoons more closely. Somebody sitting in United States will say, okay, I may not be interested to study Indian monsoons, but I will study Pacific and Atlantic oscillations in more detail, because that's what will bring rainfall to the continental American plate. So I would study those phenomena better. So what we will end up with, we will end up with multiple modeling groups coming up with their own models, producing their own time series, having their own accuracies, having their own assumptions, having their own outputs, but all done making sure that boundary conditions are met. What these boundary conditions are? You need to start from somewhere, first of all. These are called as initializations. At t equal to 0, you need to know system state, right? Otherwise, even in the differential equations that we were writing, x2 minus x1, t2 minus t1, can you solve for x2 if you don't know x1? You need a starting point. This is what we call as initializations. Then you also need to know the boundary conditions. What would be the boundary conditions here? How much carbon dioxide is present or would be present in 5 years, 10 years, 15 years, 20 years down the lane. So all these modeling groups will come and agree that we will use same boundary conditions. We will use same initialization, but equations, phenomena would be ours. And we'll study their evolution in time. Does it make sense? So what we are looking at, each modeling group running their own models, producing all the variables by themselves. So now we are classically heading towards generating lot of data. Right? Yesterday we talked about petabytes of data. So this is the genesis of that model data, that how we generate so much of model data. Does it make sense? Now question arises, which model is right and which model is wrong? Anyone? Yes. Okay. So let me rephrase it. So you say that some models may be good in some variables, other models may be good in other variables. So it really depends what variables are looking. For example, some models may be very good with precipitation. Some models may be very good with rain, humidity. Some models may be very good with wind. So really depends on the use case. Fantastic. Anybody who is sitting online would like to answer this question? How would you say that this model is right, this model is wrong, this is better, this is worse? Should we discard all the other models and just focus on one model? Should we still account for all other models? So yes. IPCC doesn't make model. Yeah. So forcing would again come from boundary condition. Forcing is same. Yes. That does not. This is the keyword. Having different model structure doesn't necessarily make them wrong. Right? They all have to be. You can weigh them. You can say that this particular model is better to study this phenomena, but you cannot discard the other models because I am as uncertain as the other model is. Had the physics been perfect, has the boundary conditions been perfect, has the underlying model equations would have been perfect, I would not need multiple modeling groups. Right? So do you use Google Maps and WISE and OpenStreetMaps at the same time? Why? There are also multiple models that tell you at what time you will arrive, but why don't you use all the three applications at same time? Why? Huh? You can feel free to speak. I'll correct if you are wrong. I'll add if you are right, something to it. Yes. Yeah, so you have one model which is quite reliable. It's not rocket science that they are resolving. If you know average speed of travel and average distance of travel, you would know at what time you will arrive, and you may not be over worried about the inaccuracies 1 or 2 minutes are going to propose, right? However, if sometimes you may see that Google Maps is not telling where obstructions are, where there is a traffic blockage, it is taking me through non-highway routes. You will say, wait a minute, I'll not use Google Maps, I'll switch to some other map, or I'll apply my own model. When you ask route from somebody, you're also doing modeling at that particular time. When you apply your brain is also applying a model to predict from which route you will reach faster. So not necessarily they are wrong, but the representation is giving certain value, which may be working fine in some cases, not working fine in some cases. But here we are dealing with so many unknowns, so we cannot just discard any other model. Now, these different models, they also produce outputs at different resolution. Somebody sitting in United States may say that I have access to 3 supercomputing facilities. I will run my model at 100-kilometer resolution. Somebody sitting in Japan would say that, see, I don't have access to 3 supercomputers. I have access to 1 supercomputer. So let me resolve these processes at little bit coarser scale. Somebody sitting in India would say that we are partnering with our partners in Germany, and that's what India is doing. So we have European partners to develop our own climate model. So they will run these particular models with similar structure, same boundary conditions, same initializations at different resolution. So you end up with models with different resolution, with different values, right? And again, we are not concerned about what is the precipitation tomorrow. We are not doing weather forecasting. We are doing climate modeling here. At the end, I would look into agreement and disagreement in statistics. What is the long-term mean? Typically 30 years. What is the long-term mean of particular variables I'm getting? So you see here, I have resolution on x-axis and different models. Again, resolution on y-axis and different models plotted in the scatter plot. Some of the models are still run at 4 degrees by 4 degrees. What these degrees are? Equator ka kya hai degree? 0 degree. If you talk about latitude, we are at approximately how many degrees? 23.5. Why? Because we have Tropic of Cancer passing from Gujarat. Perhaps if you go 50-60 kilometers, there is Sun Temple here, right? So it's in proximity of Tropic of Cancer, 23.5 degrees. So this is what degrees are. How far are we from equator in kilometers? (2,350 kilometers approximately. Multiply 1 degree by 100, you will get an approximate distance. So these resolutions essentially so there would be certain changes. Why? Because distances at poles would not be necessarily same as equator, because we have a peculiar shaped Earth, right? But on an average, 100 kilometer is a good approximation of these resolutions. So when somebody says 4-degree model, immediately multiply with 400 kilometers. That would immediately make sense to you, right? Again, one more thing simplified. So now all of us agree that system is complex, system is nonlinear, dynamical, system has a lot of uncertainties, different modeling groups putting all their efforts to come up with better representations of Earth system processes. So that makes it a classic big data problem. We indeed have a lot of data in petabytes that these models are producing, and this is important to understand what these climate resolutions are. Now, when we also look into uncertainty, so for example, here we are talking about temperature change with respect to some benchmark period. We are not interested in absolute temperature, by the way. Would you be bothered when temperature outside is 35 degrees Celsius? Would you get a heat shock if temperature outside is 35 degrees Celsius? Yes or no? No. Talk to somebody who is living in extra tropics. For them, 35 degrees Celsius is unbearable, right? Why? Because our body, our bodies are accelerometers, not speedometers. You would feel the acceleration, but not necessarily the speed. Same thing is with temperature. Same thing with other variables that surround us. We will always talk about changes. How much changes has happened with respect to something that we have already adjusted to. So that's where you will see in these reports, we always talk about changes with respect to some benchmark period. And this benchmark period is typically taken from 1880, from this plot it's 1986, but it is taken with respect to pre-industrial levels. That is 1885 was, we classify as the industrialization, I mean, started happening in Europe, and that's where greenhouse gases emerged significantly. But something we have to understand, this is the relative change with respect to the ongoing period. Again, you see the averaging over period of 1986 to 2005. How many years? कितने साल हो गए? 86 to 2005. Huh? 1920, right? Because you will also consider boundary years. So over a long period of time, mean climatological changes over a long period of time. And you see different sources of uncertainty coming into picture. Blue band represents that some models are saying that with respect to benchmark, global temperatures will increase by 1 degree Celsius. Some models are saying they will increase by 3 degrees Celsius. So that's the entire confidence band that we get just from multiple models. And this is at the end of 2100. Today is 2022. We are talking at the end of 2100. Now question arises, is this the only source of uncertainty? Where are the other places we have uncertainty in these models? Can you tell me? You feel free to use your phones, Google, whatever you want to do, right? What is the carbon dioxide concentration in atmosphere today in parts per million? Today, I mean today as in 2022, 2021, it will not fluctuate daily because it also has some cyclicity, but you will get an average value. Parts per million concentration of carbon dioxide today. Huh? 414 ppm parts per million. What would be the carbon dioxide concentration in 2050? Maybe more. At the end of 2100? We don't know. This really depends how we develop. If all countries come to an agreement that let's reduce our carbon footprints, let's find more sustainable sources of energy, let's really cut on our greenhouse gases emission. Let's invest more in carbon capture. All these are possibilities. All these are scenarios. Or countries may start fighting with each other that you already have done your development. Why you are stopping us? We'll industrialize heavily. We have been agrarian economy for last 70 years. Now we cannot sustain with that, survive with that. Let us industrialize. Right? China will say that we are in our development spree. We may not agree to your agreements. Right? United Nations exactly said that, right? We don't agree with the Paris agreements because it would be detrimental to our development. That means it is not just the matter of our assumptions as scientists. Things are more complex at policy level. Certain countries may agree, certain countries may not agree. So we may have an optimistic scenario, we may have a pessimistic scenario. And it is not going to happen that today we decide and tomorrow abruptly all countries cut down their industries or change from non-sustainable to sustainable, because there are technological limitations as well. And that is what gives rise to different scenarios in climate models. We have optimistic ones, we have pessimistic ones, we have intermediate or more realistic ones. And we call these as RCPs. Initially used to call as RCPs, important term for you to know because we'll see that how this data looks like. But now the name has been, RCPs were representative concentration pathways. We are talking about concentration. Now ppm is concentration. We are representing entire globe by one single number. Representative concentration pathway, what development pathway we will follow. So that gives the names RCPs. But then recently scientists realized that we may talk about these numbers, but what may be missing from here is the representation of socioeconomics, how people will respond, how societies will develop, how economics will grow. So we came up with more holistic terms called as SSPs, shared socio-economic pathways. And again, see the complexity now. Earth itself was complex, Earth system was complex, equations were complex, modeling groups got supercomputers. So each modeling group generated multiple variables. So that was already a big data. Now each modeling group has also to look into all the possible scenarios. So you cannot just settle with one assumption, because that would be wrong. How do you know that what is your entire band of uncertainty that you may have to deal with in future? Are you understanding what I'm saying? So one modeling group, multiple grids, multiple resolutions, multiple scenarios, multiple time periods. So this is the volume, how it has increased between 9 a.m. when we started and 10 a.m. in 1 hour. We thought it to be that a single point, but now you see that, and for each location, we will have multiple scenarios, multiple models. So these are the two primary contributors of uncertainties that we have in these models. Don't you think this will apply to any forecasting model? Not forecasting, any projection models where we don't know how things are going to develop. If somebody asks you what would be the stock price at the end of 2030, you will start from today, right? Today Sensex is at 58,000. That is your boundary initialization. You will set up some model that x of t is function of xt minus 1, t minus 2. What was Sensex at same point last year? What was Sensex at same point 2 years back? So you have thought of some model. But then you will say, wait a minute. What if more countries like Russia and Ukraine get into fight? What if there is another crisis, what we are having in Sri Lanka? What if there is more stability in Middle Eastern countries? So all these are positives and negatives. They are factors that would determine your model. So if you just say that, I don't know, I just care about my model, I have assumed that there will be peace all over, Sensex would be 1,50,000, please invest all your money. What you are doing? You're not representing uncertainty, hence designing the policies that may misguide the future development or investments. And same thing applies to climate modeling scenarios. If I take one model, one assumption, what if that particular assumption or pathway is not correct? I am going to create disaster in terms of policy making or informing policies. This is the exercise we did. I yesterday mentioned that do we really do something for real life, or we just give lectures here? We also try to go to stakeholders and do this modeling for them. So we try to understand what this would mean for Sikkim at the end of 2022, 2100. So we looked into multiple models, multiple initial conditions for state of Sikkim, and told them that this is how temperature profiles will evolve, this is how precipitation profiles will evolve. And these are super resolution products we are using, which Sarth will talk about today. But even see the band of uncertainty that we have. If you see here, these are multiple model outputs for Sikkim. This blue one was our observation, but has already happened. Then modeling outputs took over. If you see here, if we just rely on green model, we may be saying them that, see, don't worry, everything is fine. You are not going anywhere above what we have already observed. But if you see the top model, that is the red one, we will say, oh, see, everything is increasing. That is what we wanted to convey, that see, there is variability and uncertainty, but still what we notice is that all models are projecting towards some increase. All models are hinting that number of warmer nights will increase as we go towards 2100. But we cannot comment on the finite value. We cannot say it would be 2 degrees Celsius warmer, 1.5 degrees Celsius warmer. We say that with equal likeliness, they may be somewhere between 1 degree Celsius and 3 degrees Celsius. So make your policies keeping that in mind. Yeah. Absolutely. So you can construct confidence interval here. However, we have very finite samples in this particular case. So rather than doing statistics and calculating, some confidence interval may not be wise. So that's why we represent the full band of uncertainty, because we are dealing with 35 data points essentially. You can definitely construct fit a distribution and then construct a confidence interval, but may not be a wise idea given really finite number of samples we have. Does it make sense? But that may give you an asymptotic behavior. And sometimes we also do that, by the way, in extreme value theory and so on. But yes, that's exactly what it would be. And same thing applies to different scenarios. So we have multiple models and multiple scenarios. What changes in these scenarios? If you see, here I have changes in carbon dioxide concentration. Today we are standing at 20. What is this value? 415 parts per million. What did you say? 415 parts per million. Going forward, I can go this pathway, this pathway, this pathway, this pathway, this pathway. I don't know. This is what gives birth to these scenarios. More carbon dioxide, more greenhouse gases. More greenhouse gases means more trapping of heat. Speaking in layman language, more trapping of heat means more radiative forcing available for us. More radiative forcing would mean on an average warmer earth. That's why we say it's a global warming coupled with GHGs. Be it anthropogenic, be it natural. Let's not go into attribution part here. But that's how the pieces of model goes from model to carbon dioxide to temperatures and other variables of interest. Right? And these are all possible outcomes that if we take a better route, we may be looking at around 2 degrees Celsius, 1.8 degrees Celsius rise at the end of 2100. If you look at worst case scenario, you may be looking at upward of 4.5 degrees Celsius overall warming. Neither worst is realistic, nor most conservative is realistic. We may even have something out of the bounds also. Right, some serious technological intervention happens and we see serious transformations. But again, this gives us an idea that what are the ballpark numbers for which we have to plan, mitigate and adapt. But from data perspective, we are looking it as a big data problem now at our disposal. Now question arises, different modeling groups, different scenarios, different models. From where I can get this particular data, how much I have to pay for this data, what would be size of this particular data. So yesterday, many of you approached me regarding projects, not finding data. For me, data is definitely an oil, but in Middle East, where I have a lot of it. Just go to this particular website. You will get all this data for absolutely free. You can download on your computers if you have enough space to store that particular data. Let's play this small game. Can you put an estimate? If now everybody understands scenario, right? So if I download the data set, so please try to participate so that you get develop some intuition. If I want to download a data set for period of 2015 to 2100, okay, 2015 to 2100 for SSP 2.6. This essentially represents one of the pathways. Let's not worry about SSP 126. This is how it would be represented. Scenario number 1, 26 is the extra watt per meter square of insolation that would be coming because of more carbon dioxide. 128, it's not 126, it's precisely 128, 2.8 watt per meter square. What would be size of this particular data file from one modeling group? Huh? Okay, so somebody is saying few hundred GBs, greater than 100 GBs. Any other estimate? Think about it. Right now, you all have some background in computer science, how data is stored, what variable you are looking for. I'm just looking at one variable here, surface temperature. Okay, so because there would be multiple variables, so temperature at 2 meters above ground level. Again, fixing some boundary conditions. Any revision now to your estimate? Huh? 1020 GB. Okay. Any other option? How much data you need to save one number on computer? Bits, you will measure something in bits and bytes. Think in that particular term. All these data sets would be typically stored as float 16 or float 32. Now you have a lot of information with you to come up with better estimate. Huh? 300 MB. Oh man. So you have traveled a long way from 100 GB to 300 MB, which is interesting. Anybody in KBs? Right size of a song? So this would be somewhere between this actually. So this would be 3 GB. Divya, that would be good estimate. 3 GB, right? So around 3 GB, you will have one variable, one scenario, one model. Now we typically deal with 7 variables. We typically deal with 4 scenarios. We typically deal with 35 models. And each model has different initializations. So you just do simple mathematics, you immediately end up in few TBs of space. But not bad. I'm getting this much data for free for analysis, looking into these trends, looking into what it would mean for my region, my area, use that as boundary condition in my other models. So that's why I say that it's not a data scarce problem. We have a lot of data. I'm not again talking about credibility, reliability, that's a separate issue, but I have a lot of data to play with. Right. So let us go to that particular website and try to just do a quick hands-on before we move to our second part. So all I have to do now, good thing is that I wanted to go a little bit into detail or digression before I go into hands-on, so that you understand these terminologies now. Now SSP is not a surprise. Multiple models are not a surprise. Multiple initial conditions are not a surprise. Multiple scenarios are not a surprise. Right? IPCC is not a surprise. So that's why we took a bit of a detour today, which I think was must before I would have introduced you to this. Here, this is the website from where we get all our data sets. We'll share the link, don't worry, we'll put it on Discord. However, here it gives you multiple options. So if you go here, it talks about which MIP era you are going to talk about. I said multiple assessment reports come, AR1, AR2, AR3, AR4, AR5, AR6. Right now we are AR6. Right, we have prepared a 6th assessment report. IPCC has prepared 6th assessment report. So that's where it says Climate Model Intercomparison Project version 6. You can also go to CMIP 5. You can also go to CMIP 3. There was no CMIP 4. I have to look into historical reasons. But after 3, it was 5. But right, so I think they have to match the assessment report number. Perhaps that could be the reason. So CMIP 6. Here, if I go to activity, you again see a lot of models here. So DAMIP. So there may be OMIP. Anybody can tell me what is OMIP? CMIP was Climate Model Intercomparison Project. What could be OMIP? Ocean Modeling Intercomparison Project. Right. Similarly, GeoMIP would be related to Geological Modeling Intercomparison Project. High Resolution, ISMIP. So you can now relate to this terminology easily. That some modeling intercomparison project, because I said that it's not one man's or one woman's exercise to design these. People from these expertise come together, set up their models, they talk to each other through a coupler, then exchanges of data and information happens, recalibration happens. But again, good thing is that this data is available for us. So if we understand the basic nuances of data set, we are good to go to at least download this particular data. Now let's go to product. Yes, we are looking at model output. They are not talking about observations. Let's go to source ID. These are different modeling groups that are participating and have certain names. CESM is a lab, right? So CSM2, ESM is another lab. XSCM2 is a product again coming out of the lab. So these are the IDs. So XS would be a modeling group and they may have multiple models that they publish. Right, so don't get confused. Why there are so many abbreviations I have to remember. CAN ESM, कहाँ का हो सकता है ये? Canadian Earth System model. Similarly, we have MyROC. We have CSIRO coming from Australia. We have NASA's GFDL, Geofluid Dynamical Labs model. So you can imagine that entire lab working together to put one model together, how much of an effort that really would be, right? But nevertheless, let us say that I want to look into CAN ESM. I can, so these are institutes. Those were specific models. Here you see that all the institutes that are participating, right? So this is what I was saying. One is MyROC. I think MyROC is from Japan, if I'm not correct. Not wrong, huh? MyROC is from Japan. So these, we get used to these locations because we read about that what specific expertise this modeling group brings and so on. Then I want to see the nominal resolution. How many models at 10 kilometer? 447. How many models at 100 kilometer? Huh? 23 million, right? Or 2.3 million? 2.3 million models or model outputs at 100 kilometer resolution. Right? So that makes sense. Not everybody wants to run these models at super resolution, but certain modeling groups may be interested to learn some phenomena. So they took the courage to run this at 10 kilometers. Where? So that's why you have to be very careful when you save your data files with nomenclature. Right? When these modeling groups were saving the files, they might have put an extra space. And when they put the data on archives, archive would not know whether these are same or different. I hope you understand why never use spaces in your file names now. Right? This is the reason. They are essentially same resolution, same product, but perhaps somebody pressed an extra space. Somebody like me, not from computer science, wanted to save their model and added an extra space there. Okay, that could be the reason. Yes, that is very important. Thanks, Arth. So basically, there's so much data. I would not spend my life to download these data sets. I will design one wget script, identify the patterns, but sometimes it may not return any query or any results on my query because of these small nuances. That I wanted 100 kilometer, but they have 100 space kilometer. Right? So we'll also see how that wget scripts would look like when we make certain clicks. Here are the experiment IDs. This is where I want you to show. Can you see these phases now? SSP 126. Right? What is this? SSP 245 COVID. Huh? Okay, but they essentially represent the boundary conditions. So what happened during COVID to emissions? There was a sudden dip. Perhaps they included one of their scenarios to capture those boundary conditions, change the boundary conditions because of that event that has happened, and rerun all these particular models. Make sense? So now you're familiar with one of the most complex data repositories out there in Earth systems. Right? Now you can make a lot of sense. Now it's not a surprise, right? SSP 245 COV fossil, mod green, STR green. So they represent very specific development scenarios or changes in conditions that these models are talking about, but all wrapped around SSP 245 structure. SSP 245 is telling us boundary conditions. They made certain changes to boundary conditions, but making sure that 2100 goals are still followed from SSP 245. Pathways is still SSP 245. Slopes of changes are still coming from 245. But these are the scenarios that they will have. What is this? Volcano Pinatubo full. So they might have tried to include changes in boundary conditions or scenarios as a result of volcanic eruption. Volcanoes will also give us a lot of greenhouse gases in upper atmosphere. So again, scientists follow logic. It's nothing come out of the box, right? So they say that, okay, 1 to 6 is fine, but what if a volcanic activity starts and continues for a period of time? Or once it has terminated, how the emission conditions will change? So that's what these scenarios give us. Then you need not worry about these sub experiments variant labels at this particular stage. But I have to worry about variable, and I should show this to you. If you see, these are the variables here. Again, you don't have to remember them. When you start using them, I would know. Let me not give you too much of an information, take you something that you recognize. Yes, here we are. What this could be? TASMAX. Huh? Temperature. Temperature at surface, maximum temperature. Rather than talking about average temperature, they may be talking about maximum temperature. What's above that? TAS. It could be surface temperature. Similarly, you will find a variable PR, which would be precipitation, and so on. So these are the variables that you can relate. So same model solved by multiple modeling groups thrown here, and now you can, let us just select this TAS min and see what the search yields. I have not done the selection appropriately, but so it will show a lot of results. Now it is telling me that for CMIP6, for CMIP, I have CAN ESM data for this particular run, 1% carbon dioxide for this particular initial condition. And now if you build a right set of queries, knowing what data you want, it will only show the options of your specific model, specific scenario, specific variable, now which you can download. As soon as I'm getting here, you see certain options here, show metadata, list files, W gets stripped, and so on. So I will first say that please list the files you have. Can you see this particular extension? What is this? Dot NC. Now what the heck is this? Are you dealing with time series data here? Yes or no? Is it time series data? Come on, feel free to answer. Why it's a time series data? Every day it will have some value. For every day, average, maximum, minimum, if it's a daily data, it will have value every day. Is it a spatial data? It is a spatio-temporal data. How you will save this particular data? You will have stacks of, is it a global data? Yes, it's a global data. I have not specified any region. It's an output from a global circulation model, general circulation models. How would I save this data? Think again logically, forget about NetCDF. I will draw a map of world, put values, whatever I need to put. I will stack them together. What I will end up with? I will end up with a box having multiple layers or slices in space and time. If I have multiple variables, I will put boxes on top of each other. I have stacks, multiple stacks now. One way to save them is how you would save it in Python, for example. Huh? It's a data frame. Data frame may be very complex. Why? Because there would be so many repeated values, because now indexing is going to be difficult. So we came up with very neat format to save these data sets called as netcdf files, where you can build a query on space, time, location, get the map out of it, do the analysis, dump the analysis back in netcdf files. And this is what Sarth will do in our lab session today, where we will actually download one of the files, show you how netcdf file look like, how to process it, how to plot it, how to put your analysis back, and publish it again as netcdf file. So I hope all of you feel more comfortable that this data is now within our reach. We can download it, and once you click on download, it will start downloading. So you have to do certain formalities, register, login into their website. So they will ask for username and password, a typical data downloading system which they have put on their website, but your download will start. So they have again divided files into smaller chunks. Typical size would be 1.23 GB, and then you can stitch them together to get your full time series. Does it make sense? But only download if you have reliable internet connection and some space on your computer. Now the problem still remains the same. I am not running these models at super resolution. I want to understand difference between Ahmedabad and Gandhinagar, and 100-kilometer grid will not do the work for me. Still, they would be part of the same grid. How do I do that? That's where I have to do some machine learning. That's where I have to identify some patterns, that how data or observations here are related to my model outputs at coarser resolution. Right? And we essentially say that this is the problem of downscaling. In computer vision, terms are interchanged, by the way. They call it upscaling. Climate scientists call it downscaling, but things are same. Right? We are trying to increase the resolution of data set. How you will increase resolution? Don't think like an engineer or scientist, but think like a layman again. How you would increase resolution? Can you watch a 4K movie on 720p laptop? Yes or no? Arey, participate. Come on. This is a very simple question. Beyond climate. Come on. Yes. तो फिर 4K टीवी क्यों खरीदना? क्या होगा रेजोल्यूशन से? What is quality? Come on, articulate it. What is quality? पिक्सल डेंसिटी ज्यादा होगी तो क्या होगा? विराट कोहली का चौक का छक्का बन जाएगा? हाँ, शार्प होगा. What sharpness means? More details. जहां पर एक बॉल आपको दिख रही है, अब आपको हो सकता है कि जो बॉल की सीम है वो भी दिखे. When you talk about 8K, हो सकता है अगर सीम का कोई धागा बाहर निकला हुआ है वो भी दिखे. You may talk 16K, then हो सकता है कि उसके माइक्रो स्ट्रक्चर्स भी दिखने लग जाए. So what is happening when you are watching 4K movie on 720p screen? What is happening? Some interpolation will happen, some loss of information will happen. So जो घास होगी ground पर, that may still appear like a grass, but it will lose all the details because some smoothing will happen because pixel size mismatch is there. So that's what simple interpolation is in our world. However, if I have to really watch 4K movie on my 720p device, how I should do that? I still want to do that. What should I do? क्या करूं? नया कंप्यूटर नहीं खरीद सकता, नया फोन नहीं खरीद सकता, सेम डिवाइस है, सेम डेटा है, सेम मूवी मुझे देखनी ही देखनी है. और मुझे घास के फाइबर भी देखने हैं, मुझे बॉल की सीम भी देखनी है और पैसा भी नहीं खर्च करना. पार्ट्स में डिवाइड करेंगे, एक्सीलेंट. एक पार्ट पे फोकस करेंगे और उसको ट्रेन करेंगे कि उस पे जो कोर्स है, दिस इज द हाउ फाइनल शुड लुक. सो आई विल जस्ट फोकस ऑन दैट पर्टिकुलर पार्ट, add more information and details, but only focus on that particular part. That's what I will essentially do. And this is what climate downscaling is. You have to add more information as you interpolate. If you remove the information content from it, just do interpolation, you are simply doing smoothing, which will result in loss of information. And it may not have any more information content. I'm talking this in I mean information just to relate to that, not the information theory information, but more information in terms of the variable, mean, standard deviations, averages, other statistics. Only what the coarser resolution will have, it would not be able to have anything specific to Gandhinagar. It would still be Ahmedabad's information just transferred here. or average with the nearest grid points and giving you a smoothened expression for Gandhinagar. Does it make sense to you? So how we will do that? We will try to learn that how the X at the surrounding grids relate to my Y, which could be observation at Gandhinagar. I will try to understand how precipitation at Gandhinagar is function of output from model that was set at Ahmedabad with one grid point in Surat, with one grid point in Vadodara, with one grid point in Mumbai, with one grid point in Madhya Pradesh, because that's the resolution I have. But I have made some observations for Gandhinagar. So I would like to ideally develop some relationship, a regression relationship between how my Y, which is my variable of interest, relates to the information I already have. Can I use linear regression to do that? Yes or no? Why no? I will start from linear regression. Would it suffice? Maybe not, because we started, these models are nonlinear, dynamical, simultaneous systems. Processes may not be linear, so linear representations would not work in most of the cases. Huh? We can, so that's, now we'll eventually talk about nonlinear methods and so on. Yesterday it rained in Ahmedabad. Do you think it will impact weather of Gandhinagar today? Could be. It rained 5 days before in Mumbai. Do you think it will impact weather at Gandhinagar? Yes. It rained on 1st of May in Kerala. Do you think it will impact our weather today? Very less chances. But one thing you have just told me, that it's a problem in space. It's a problem in time. Now we have to identify patterns in space and time. So whatever learning we do, it has to be in space and time. Would weather of Gandhinagar today would depend what happened yesterday in Gandhinagar? So that means it's autocorrelated also. It's a problem in space and it's a problem in time. So when word space comes to you in learning, what is the first thing you would think about? Which approach you would typically prefer using? Huh? Any idea? Quadrants, something to do with quadrants, something to do with grids. कौन सी machine learning approach है, deep learning approach है that may be useful when you are doing learning in space? Convolution neural networks कर सकते हैं ना? When it comes to recurrence time, LSTMs. Can we combine LSTMs and CNNs and talk about convolutional recurrent neural networks, which we will certainly do. By the way, this is one of the many ways to do this particular downscaling. People have been using physics-based models. Ki theek hai, we'll take boundary conditions from those GCMs and run again the same model for smaller grid size. Possible, because now we are just focused on Gandhinagar. Why to run the model, climate model for entire globe? Let me use my computer and run it for 5 or 6 or 7 grids with boundary conditions being coming from climate models. Possible, and these are called as RCMs, regional climate models. But in this particular class, we are going to focus on GCMs and various machine learning approaches, that how we can generate the finer resolution. I started with the word computer vision. We have drawn this inspiration from computer vision. Not long ago, in 2016, one of my peers now who works at NASA Ames developed this algorithm, that how we can use downscaling, how we can take this super resolution architecture, which is well established in field of computer vision, for climate downscaling. Last year, one of my BTech students, Nidhin, computer science student, we realized that it may be an interesting problem, but it fails to interest climate scientists because of the fallacies it introduced, because it's not a super resolution problem. So we came up with the next step of architecture, and that's how science progresses. But that's how this entire thought process started, taking inspiration from climate from computer vision and applying it to climate. For example, if you see first problem that people typically do in machine learning courses would be a cat and a dog problem. You have a photograph. Can you classify it as a cat or a dog? We hypothesize that don't we see similar patterns when cyclonic formations develop? Can wind patterns be classified as cyclonic, non-cyclonic, extreme, non-extreme? Another problem that people do, that is take a blur image, generate a high quality image. In fact, now you can also convert your age-old albums to high resolution ones. Of course, by paying some money. How you would do that? Image super resolution. It would learn from multiple samples that our nose of somebody coming from India, coming from North India, coming from this particular origin would look like, and then they will try to come up with the best approximation. We said, cannot we apply the same kind of thinking and do single image super resolution to climate systems where we have observations at coarser scale, how they would look at finer scale? However, we are not interested in static system. It's a dynamical system. Then we drew inspiration from video frames. If you have multiple frames in the video, you can now really predict what would be the next time step just by using these learning in space and time. Isn't it the problem same as climate systems? That if you have observations in space and time and you really want to project how they are going to relate to what is going to happen at next time step. So that's how it comes into action. And of course, LSTMs, they help us do simple time series forecasting and so on. But this is how we open the doors to super resolution approaches using convolutional LSTMs for climate models. So we'll talk in more detail about that when we meet again today at 4. Please bring your laptops. That's how is the practice, I believe, where you would be running your notebooks. We have designed an end-to-end notebook for you. You will do learning. It's a Google Colab notebook. So please come prepared, and then we will talk about more specifics of these particular models. If you have any questions, this is a good time to ask, because when you come to the lab, come with an expectation that when you leave, you should know how to handle this NC file end to end, differences between interpolation and super resolution, and how we incorporate space and time in our learning to get some meaningful output, and how we validate. Does it make sense? All right. Thank you.